Hey guys, welcome back. All I have for you today is the solutions to the part 2 for the practice midterm. So there is still 46% of you guys that have not taken that. So we don't have an assignment today on Wednesday. I'm trying not to give you guys assignments on Wednesday just to give you a bit of a break. But of course it takes me an extra day to roll out these videos for the solutions because I have to wait for the data to be collected. So make sure that you are going through the videos is really all you have to do today, at least from my class. So it's a good way to review and make sure that we are figuring out what we're doing wrong on the practice midterm. The practice midterms that I'm giving, they're just worth, it's a completion grade, like a homework grade, but they still, it's important that you do them because they're getting you ready for the midterm, which will actually replace your test scores. So make sure that you understand how to do this stuff. Number one, only 18% of you guys missed this, so good job. Determine if the following conjecture is true or false. If false, give a counterexample. So if it is a bird, then it can fly. Now, in general, that is pretty true. Most of the time birds fly, but the real question we have is this statement always true? So if it is a bird, does it mean that it can fly? So the real question we're asking is there flightless birds? And if there are flightless birds that cannot fly, then that would be a counterexample to the statement, because the statement is implying that all birds can fly. So is that statement true? All birds can fly? No, clearly not. Penguins, for example, are birds, but they cannot fly. So that would be our counterexample, which would be C as in Charlie. Yeah, so it doesn't matter. We're not saying that everything can fly that flies is a bird. That would be the converse of this statement. We'll look at that on the next question. So Peter Pan can fly, but he's not a bird. That doesn't matter. Butterflies can fly, but they're not birds. That doesn't matter either. And the statement is not, it is sometimes true, but it's not always true. And so it's a false statement if it's not always true. Okay, so our counterexample are flightless birds, which are penguins, for example. All right, number two, it says, is the following conjecture a good definition? So in order to be a good definition, it has to be reversible, meaning the conditional and the converse of the statement have to be true. In other words, it goes both directions. Then it would be a true biconditional statement and a proper definition. So the statement they gave is, if you live in Oklahoma City, if and only if you live in Oklahoma. So that statement, the converse or the conditional of the statement is that if you live in Oklahoma City, that's a subset of the people who live in Oklahoma. That statement is true because Oklahoma City, I mean, even graphically, is entirely inside Oklahoma, unlike Kansas City, for example, which is in two different states. Okay, so if you live in Oklahoma City, then you live in Oklahoma. That is true. So the conditional statement is true. I got no problem with that. But the question is, if it's a good definition, then it will be reversible. So what about the converse of the statement when I switch the order? If you live in Oklahoma, does that mean that you have to live in Oklahoma City? No, that's not true. There are many cities and towns that are in Oklahoma that are not Oklahoma City. The Oklahoma City metro area is very large, but it's not the entire state. So the converse of the statement is false. So this is not truly a reversible statement, so it's not a good definition. It is a description. So if you live in Oklahoma City, you do live in Oklahoma. That's a description of what it means to live in Oklahoma City, but we can't define living in Oklahoma by living in Oklahoma City. Those are not the same thing. So they are indeed a proper subset instead of an improper one. They're not the same set of people who live in Oklahoma or same set of people who live in Oklahoma City. So it's not actually a true biconditional statement. And so the reason that this is not a good definition is because the converse of the statement is false. So the converse of the statement is false, which would be D as in delta. So no, it is not, because the converse of the statement is false. So a lot of the confusion here is you said yes because the conditional of the statement is true. So yes, the conditional is true, but in order for it to be a good definition, instead of just simply a description, it has to be reversible. It has to be true in both directions, and the converse was not true. So make sure that you understand this. I suppose I could have done a better job of teaching it, but it is a very important topic that I want to make sure you guys understand. So for it to be a good definition, it has to be reversible, a biconditional statement which goes both directions. All right, number three, use the law of detachment to draw a conclusion about the two given statements. So if two angles are complementary, then their measures add up to 90 degrees. So angle 1 and angle 2, they add up to 90 degrees if it is complementary. I suppose I should give the line here to show that those are right angles. Okay, so if they're right angles, if they're complementary, then their measurements add up to 90 degrees. All right, then they tell us that P and Q are complementary. Well, if P and Q are two angles that are complementary, then that means by the law of detachment, they said any angles that are complementary, their measures add up to 90. Well, if P and Q are complementary, then what do we know? Their measures have to add up to 90. So the measurement of P plus the measurement of Q has to be equal to 90 degrees, which is alpha. All right, so most of you guys got that right. Good job. Law of syllogism, so this is our other form of deductive reasoning, is basically like the transitive property. So if A goes to B and B goes to C, then we can skip from A over B and go straight to C. So A goes to C. Okay, just like the transitive property. So if it's a multiple, and I color code it so you can clearly see what's going on. So if multiple of 8, it's a multiple of 4. If it's a multiple of 4, then it's a multiple of 2. So if it's a multiple of 8, then it has to be a multiple of 2, which would be A as an alpha. So pretty much all of you guys got that right too. Good. What's the inverse of the following conditional? So if a number is divisible by 20, then it's divisible by 5. So the inverse is when we negate it. So we're going to keep the order the same. We're just going to put knots in front of it. So that would be if it's not divisible by 20, then it's not divisible by 5. I should have color coded that one. It bugs me. I have to. All right, so our answer is B as in Bravo. Good job. What's a contrapositive? So the contrapositive is the longest one. That's where we negate it and we switch the order. So we're doing the inverse and the converse. So we're going to start out with this 8x is 72, but we're going to negate it. So we're going to say 8x is not equal to 72. Then x is not equal to 9. So we just switch the order of the p and the q and we negate them. So that would be C as in Charlie. Ouch, Charlie, that really, I can't not do it now. I'm sorry. All right, what is the converse of the following conditional statement? If you live in Dallas, then you live in Texas. So the converse, all we do is switch the order like shoes on the wrong feet. So if you live in Texas, then you live in Dallas. If you be in Bravo. You guys are doing really well with those statements. Like, I'm impressed. Keep up the good work. 8. If write the definition as a biconditional. So to write it as a biconditional means we keep the order the same for the conditional statement. We just put if and only if in the middle. So they're saying a composite number has more than 2 factors. So if our conditional statement would be if it's composite, then it has more than 2 factors. So part A here, that's actually the conditional. But to write it as a biconditional, what we do is we get rid of the if and the then, and we use IFF in the middle, if and only if. So we'd say a number is composite if and only if it has more than 2 factors, which is exactly what we have for C down here for Charlie. There we go. Most of you guys got that right too. All right, complete the algebraic proof. So the first part was given to us. That's fine. Then we combined like terms. We added those together. No big deal. Then the next thing, it looks like we're subtracting the 4x from both sides to get negative x. So it's going to be subtraction property of equality. So whatever we do on one side, we do the other side to keep it balanced and equal the entire time. Then after that, we're going from 12 to negative 12 and from negative x to positive x. So what we're doing is we're actually dividing by negative 1. So this is the division property of equality. So our answer would be C as in Charlie. For some reason, a lot of you guys thought it was D, which is the reflexive property. Now, the reflexive property is like the creepy baby photo, where things like a reflection is equal to itself, right? Things are equal to themselves. So A is equal to A, baby is equal to baby. So 12 would be equal to 12, I guess, would be the reflection property. But in this case, we're actually dividing both sides by negative 1 because the sign is changing. So this is the division property of equality. The other one that kind of confuses people is the symmetric property. Symmetric. So symmetric property says that if A is equal to B, then we know that B is equal to A. Look at that lovely B right there. So the symmetric property is kind of like the commutative property, but we're switching it about the equal sign. So symmetric and reflexive are commonly mistake, but we're not even switching the order of the 12 and the negative x. We're simply dividing it by negative 1 on both sides. So anyway, quite a bit of confusion on that one, but shouldn't be that bad. All right, number 10, complete the following proof. Given AC is equal to 130, prove x is equal to 15. So the first part, we have AB plus BC is AC. So AB plus BC is equal to the whole thing, which is AC. That is a segment addition postulate. Remember the review that we did on Monday with reviewing Unit 1. So segment addition postulate, angle addition postulate. Make sure you know those because those are fair game for me to use in the proof. Like I did here. So then the next step is we plugged in all the values. So for AB, BC, and AC, which they told us was given. So that would be substitution. And then after that, combine like terms, subtract from both sides, divide both sides. So the last part here, that's pretty typical. You see that a lot on proofs. But we started the proof out with segment addition postulate and substitution. So our answer is A. The rest of you guys that mixed this up, they didn't give this information to us. That was the segment addition postulate. The only thing that was given was AC was 130, which I see how you might think that, but we were really substituting the values in. So no big deal. All right, so that is it. I will see you guys later. Under 10 minutes again. So awesome. See ya.